Okay, so we ended off looking at this bucket of water question being whirled around in a vertical circle, okay? And we decided it's possible for me to do that and not get wet, okay, as long as I make the bucket go fast enough that the inertia of the water pins it to the bottom of the bucket, okay? The bucket, of course, pushes on the water towards the center of the circle, okay? And that's what keeps it moving in the circle and keeps it pinned to the bottom of the bucket, okay? And all of that. Now, if the rope is to break, or the handle is to come off, which is why I don't do the demo anymore, okay, what will happen to the bucket? Yeah, it'll fly off in a straight line at whatever point the rope breaks. Where is the rope or handle most likely to break? At the bottom, because that's where it has to pull the hardest. Not only is the bucket's inertia trying to make it leave the circle, but that is also where gravity most directly opposes the centripetal force. Okay? Because the centripetal force at the bottom of the circle is straight up, and the force of gravity is obviously straight down. Everywhere else, there's some small angle between them, and they're not directly opposed to each other. Right? But obviously, right there is where that handle or rope is most likely to fail. Okay? And so we have to be mindful of that. If this was a roller coaster on a track, then obviously this is where we would feel the heaviest, because the track would be pushing hardest on us at the bottom. Okay, making us feel very, very heavy. All right, so we did that one there last week, but I don't think we got to these two questions here. So I want you guys to try and do question number 1, which is dealing with the top of the circle. Okay, now I will try and make that a little bit bigger. You can only make it so big before it's going to take up too much room. Okay. So they want you to calculate the tension in the rope, okay, at position A, that's at the top of the circle. All right, so remember that the information you're given is that the radius is 0.75 meters, okay, and the mass of the bucket is 1.5 kilograms, and the speed of the bucket at that point is 3.0 meters per second. Now, this is the kind of artificial thing about this question. They're saying that the speed of the bucket at any point in the circle is 3.00 meters per second. Is that possible for a vertical circle? It's not, but they were lazy. Okay? They should have really said at the bottom of the circle it's 3, at the top of the circle it's whatever the minimum speed is, okay, or whatever it is. Okay, but we're just going to say at the top of the circle it's moving at 3 meters per second. Okay, so you need to calculate the tension in the rope at position A. Remember this as well. For a vertical circle, forces in minus forces out. Okay. Good. All right. At the top of a vertical circle, okay, you have to be going fast enough that you don't fall out of it. Okay. Since this question mentions nothing about minimum speed, I have to assume I'm going faster than that. Okay. If I'm going faster than the minimum speed, then I have two forces that are acting in to the circle. Gravity being the most obvious one, and what's the other? The tension, yeah. I mean, if we're being asked to solve for tension, it has to be a non-zero value. Would you agree? They're not going to ask me to solve for something that's not there. Okay? So, the tension would be the other force. They're both in. Are there any forces out in this situation? There aren't. Okay? There are no forces acting out when you're on the inside of the top of a vertical circle. Okay? So I've got Fc equals forces in, that would be force of gravity plus the tension, minus the forces out. There aren't any. Okay, so I'm just looking for the tension, which means I'm going to subtract force of gravity over to the other side. So Fc minus Fg equals tension. All right. So I'm going to have mv squared over r, okay, minus m times g. Okay, and that'll be 0.75 times 3 squared over, sorry, not 0.75, 1.5. I got the mass and the radius mixed up there. 1.5 times 3 squared divided by 0.75 plus, or sorry, not plus, minus 1.5 times 9.81. Okay. So when I do that, I should get 3.3 newtons well, they've got down here, but I mean, towards the center of the circle would also be acceptable as a vector. Okay, everybody all right with that one? So a little bit tricky there. And then we have to remember how the top of the vertical circle works. Okay, I want you guys to try number 3. Okay, so we have a 0.9 kilogram rock attached to a 0.4 meter rope, okay, spun in a vertical circle. Tension on the rope when the rock is at the top is 79.0 newtons down. What's the speed of the rock? So we're dealing with the same position as question 1, right? So you can take some stuff from what's on the board here to help you, okay, but slightly different numbers, okay. All right, so for question number 3, okay, we are talking about the top of the vertical circle. So we got a rock, okay, on this string or rope or whatever it is, okay, that is 0.40 meters long. Okay, there are 2 forces acting on it: the tension in the rope and the force of gravity, okay, that is obviously pulling it downwards as well. All right, so Fc always equals forces in, that would be gravity and tension, okay, minus forces out. There aren't any in this situation. So we're looking for the tension again. Or sorry, we're not looking for the tension. We know the tension. We're looking for the speed of the rock. So now what I actually have to do is put in all my formulas. So mv squared over r equals m times g plus t. All right, I want to get v by itself, so I need to multiply both sides by r. Here's the trick. I need to bracket this. Because if I don't, I just punch it into my calculator, I don't get the right answer. Okay, because obviously it multiplies t by r and then adds that to m times g, which is not the same as doing what's in brackets first and then multiplying by r. Okay, so I've got that moved over, and then I divide by m. That does not make m cancel here. This is part of another operation that's being done first. Okay, so m doesn't cancel. All right, then I have to take the square root of that, okay, in order to get v. About as complex a manipulation as you're going to have, okay, for a vertical circular motion question. So v is going to be the square root of, okay, the mass, which was 0.98, okay, times 9.81, right, plus the tension in the rope, which was 79 newtons, times the radius, which was 0.4 meters, divided by 0.98. All right, so when we punch that into our calculator, I got a new calculator. I don't know if I showed you guys that yesterday. It's not very cool, but it works. Okay, so we've got the square root of 0.98 times 9.81 plus 79 times 0.4, and then divide that by 0.98. All right, so we should get 6.0 meters per second for our answer. Okay, everybody okay with that? Okay, cool. All right, that one we don't want to do. All right, we talked about artificial gravity the other day. Okay, so I want you to try question number 1. Okay, I'll make it a little bit bigger here. Space station shaped like a wheel, used to create artificial gravity. Astronauts would work on the rim of the station as it spins. Radius of the station's 30 meters. What would its frequency have to be in order to simulate the gravity of Earth? Okay, that one's going to take a little bit of thinking. There's 2 steps there. Okay, you're going to first calculate one thing and then use that to calculate the frequency after that. All right, so I'm going to give you a few minutes on that one and see how you do with that. If you get that one done, don't worry about number 2. Just worry about number 1 for now because it's artificial gravity. So what are our givens in this question? All we know right now is that we want g to be 9.81 meters per second squared, and we have a radius of 30.0 meters. Okay? Now, they want us to calculate the frequency of the revolution of the space station. Okay? For artificial gravity, I want the centripetal force being produced by the spinning drum to feel like the force of gravity at home. Okay? That's how all artificial gravity sets up. Fc equals Fg. All right? if you want it to feel like half gravity, then you just plug in half of 9.81 for g. Okay? Because you could get a question where you have a spinning space station, but they want to simulate Mars gravity. So you would spin it at whatever rate to get the g for Mars, which is about 1/3 of Earth. All right? So you keep all of those things in mind. Okay? Or if you're on your way home from Mars and you want to look like really buff when you get back, you crank it up and you make it like 2G and you walk around in 2G all the time, and you'd have to work pretty hard. Of course, there might be a problem with passing out all the time, but small problems. Okay. All right, so we got mv squared over r equals m times g. Now, F isn't in here. Okay, I can do this in 2 steps or I can do it in 1 step. All right, I'm going to show you the 2 steps first, and then I'm going to show you the 1 step because it would be quicker if you did it this way. All right, the 2-step way is to solve for v. So I'm going to multiply both sides by r, m's going to cancel, and I'm going to square root, okay, and I'm going to have v. And v will be the square root of 9.81 times 30. All right, so I got square root of 9.81 times 30. All right, so the speed of the station is 17.15 meters per second, 17.16, but I'm going to keep all those decimals. All right, now from there, I remember that v equals 2 pi r over t. They don't want me to find t, they want me to find f. So I remember this, f equals 1 over t, okay? I can just take t out of here, take this line out of here, and say that v equals 2 pi r times f, and just solve for f by dividing both sides by 2 pi r. Okay? That'll give me f, so I'll have my 17.15 divided by 2 times pi times 30 meters. Okay? And when I do that, I should get 0.091 hertz. Okay? So it makes like just slightly less than 1/10 of a rotation per second. Okay, everybody all right with that? Okay, the short way to do this involves substitution. All right, now I've told you about this substitution thing before, okay, but we do need to be aware that it exists and that we're going to have to do it at some point. All right, so I have mv squared over r equals m times g. The formula I want that has f in it is v equals 2 pi r times f. Okay? I want to plug this directly in to this formula for v. All right? But in order to do that, what do I have to do to all of this? Square it, because v is squared in that formula. So what I end up with is m 4 pi squared times r squared times f squared over r. What happens to these 2 r's? They cancel. All right, so I've got m 4 pi squared r times f squared equals m times g. Now I can solve for f directly. All right, I'm just going to have my m's cancel, okay, divide both sides by 4 pi squared, okay, times r, and then square root that, okay, and that will give me f. Okay, if I plug that in, I should get the same answer I got just a minute ago. Okay, so if I have the square root of 9.81 divided by 4 pi. Squared. Okay, I get the same answer they got, right? But I did it in 1 step with substitution, right? If that's intimidating you, you're going to have to practice it, okay? You're going to run into questions dealing with force of gravity that will involve you having to substitute. There'll be no way around it, right? So we're going to have to learn how to do that. Why did I square everything? Because in the formula, this solves for v, right? This formula here solves for v. In my formula, v is squared. So if I'm taking v, which is 2 pi r times f, I have to square it all before I can substitute it in for v squared. Yeah? All right. Try that one. This is a thinker. Okay? It's actually mathematically quite simple, but it's a bit of a thinker. Right? So you've got a roller coaster traveling through a 35-meter loop. The riders feel 2 times heavier than normal at the bottom of the loop. Okay? We're trying to figure out how fast they're going. Now, what force do you feel? Gravity or normal force? Normal force. Okay. They feel 2 times heavier than normal. Okay. That's what you have to think about here. Okay. Normally, Fn is equal to a certain other force. They feel 2 times that. Okay. Let you think about that one for a few minutes. Okay, so try this one. Okay, we're going over the top of the vertical circle. Okay, and anybody who was at home today, sorry, I forgot to record this. Here's the answer for the roller coaster question. Okay, the key there was Fn was 2 times the gravity because they felt 2 times heavier than normal. Okay, back to that one. Give that one a try. All right, going over the top of a vertical circle. Force of gravity pulls down, apparent weight or normal force pushes up. In this situation, this person going to feel lighter or heavier? We watched that video of the plane always going over the top of the vertical circle was where they felt weightless. So anytime you go over the top of a vertical circle, you're going to feel lighter, not necessarily weightless. You have to go fast enough to feel weightless. Okay? But you'd certainly feel lighter than normal anytime you go over the top of a vertical circle. All right, so here's what we have to remember. Fc equals forces in minus forces out. We've got our free body diagram identifying which force is in and which force is out. So Fc equals the force in, gravity, minus the force out, normal force. Okay? We're looking for normal force. We're looking for their apparent weight. I don't want to solve for it as a negative, so I'm going to add it over here. So Fn plus Fg equals, or sorry, Fc equals Fg, and then I'm going to subtract Fc over to this side. All right, so normal force is going to equal m times g minus mv squared over r. All right, so that'll be 75 times 9.81, because it was a 75 kilogram person, minus 75 times 22 squared. That was their speed. Okay, divided by the radius of the circle, which was 150 meters. All right, so we predicted this person should feel lighter than normal. All right, so we've got 75 times 9.81, okay, minus 75 times 22 squared divided by 150. All right, so they should have an apparent weight of 4.9 times 10 to the 2 newtons, which is lighter than they would normally be. Okay, because normally they'd be somewhere in the neighborhood of about 700 newtons. Right, so this is definitely lighter than normal. Okay, this is how all vertical circular motion problems work. Okay, you have to identify the forces in and forces out using what effectively amounts to a free body diagram. Okay, get that formula set up, and you're either going to be solving for some part of mv squared over r, or you're going to be solving for the apparent weight. There's really only a couple of ways those questions can go. Okay, what you have to remember is which forces are in, which forces are out, how are you going to feel in each one of those situations so you have some kind of context for attacking the question. Okay, questions on that one? All right. So this one's about the vomit comet. We saw that in the video the other day. Okay, plane that flies over the top of the vertical circle. Okay, how big of a circle? What are we looking for? Radius. Okay, does NASA's Vomit Comet have to fly in to give its riders a feeling of apparent weightlessness if it can fly at 210 meters per second? I am giving you one number to solve this problem with, and it's all I have to give you, because obviously we know NASA is on Earth. So there's kind of another given. All right, see how you do with that one. Okay, the little tip I'm going to give you is this. If you feel apparently weightless, what value should you assign to your apparent weight? Right? If you have no apparent weight, you're apparently weightless. You have no apparent weight, okay? Which means Fn should be a big fat 0. Okay? You have no normal force because you are apparently weightless. So there's a little tip for it. Okay? That will simplify the math a great deal on that one. So, what the Vomit Comet does is flies over the top of a vertical circle. I'm drawing it as a cart because I'm not going to attempt to draw a plane. They can't draw. Okay? So, going over the top of a vertical circle, I still have a force of gravity that is pulling me down towards the center, but if I am apparently weightless, I have no apparent weight, and thus normal force is 0. Okay? So I'm left with this. Fc equals forces in minus forces out, but the only force out is 0. I don't have any apparent weight. Right? So I'm back to this. Fc equals Fg, okay? mv squared over r equals m times g, right? And we're looking for the radius on this one. So I'm going to multiply both sides by r to get it off the bottom. Okay? Then divide both sides by m times g, and g will cancel. And I'll be left with this. R equals v squared over g. Okay? So that's going to be 210 squared divided by 9.81. Is this a big circle? It's a plane. I mean, it can't fly in a tight circle. Okay? So it's going to be a big circle. So we're looking at 210 squared divided by 9.81. All right, so it's a 4.5 kilometer radius circle. Times 10 to the 3 meters. We could have also written we could have just written 4.5 kilometers. That would have also had 2 significant digits and been fine as an answer. Okay, are these starting to make some sense? Right, very, very typical vertical circular motion questions. All right, what I want you to do now, guys, is try the ones that are in your workbook, your digital workbook. Come on. Whoa, why did that come down there? Okay, so we are looking here at the bottom of page 6, or sorry, bottom of page 2. Okay, bottom of page 2 and page 3. Okay, we've got all of our vertical circular motion problems there. Okay, so your practice problems. You will have a quiz tomorrow. Okay, and it will have it could be anything from the first few lessons here. So it could be uniform, artificial gravity, or vertical circles. I will post the quiz tonight. Okay, so you get an idea of what that's going to look like. You may. All right, so for number 3, we have a student who has a weight of 655 newtons. What force is weight? Force of gravity. Okay, apparent weight is normal force. Weight is just force of gravity. So we know Fg is 655 newtons. While she's riding a roller coaster, she has an apparent weight, that would be Fn, okay, of 1.95 times 10 to the 3 newtons, okay, at the bottom of a dip that has a radius of 18 meters. Okay, what's the speed of the roller coaster? All right, so we know in this question we're dealing with this situation where normal force is acting in, gravity is acting out. Okay, so Fc is going to equal forces in minus forces out. Okay. Since we know both of those numbers, we can go straight to mv squared over r equals 1,950 minus 655. Now, right now, I don't have her mass. Can I get it? I can, because usually we calculate FG by going m times g. So I just need to go 655 divided by 9.81, okay? And I will have her mass, which I'm going to need if I want to calculate the speed of the roller coaster. All right, so do that right now. Okay, so 655 divided by 9.81. All right, so there's her mass, 66.76 kilograms. All right, now that I've got that, okay, I'm going to manipulate here for V. All right, so I'm going to multiply both sides by R. Remember that that needs to be bracketed when you do that. Otherwise, your calculator will do order of operations, and you don't want it to. Okay, divide both sides by mass, okay, and square root. All right, so V is going to be the square root of 1,950 minus 655 times 18 divided by 67 kilograms, or whatever it was, 66 kilograms. Okay, so when we do that, we should get 18.8 meters per second. Any other ones giving us trouble? Okay, keep going then. This is doing good.